So this is just for fun, just to get you in the right mood. Genies and pool balls. So there's an infinite number of genies and there's an infinite number of pool balls, and there's this bag that can hold all the pool balls. At 1 minute to midnight, the genies put the first ball in the bag. Okay, they put ball number 1 in the bag. At a half minute to midnight, they put number 2 in the bag. At a third of the minute to midnight, they put in ball number 3 in the bag. Number 1, number 2, number 3, and they keep on going like this. Okay, how many balls are in there at midnight? What balls are in there at midnight? In the bag at midnight? Like how heavy is the bag? Or Luke.
I'm going to say infinite.
Infinite, yeah, right? So, right, all the balls, you've got this infinite sequence of balls, right? 1, 2, 3, blah, blah, right? And so all the balls are in there at midnight, okay? What if they do it this way? At 1 minute to midnight, they put in ball number 1. At 1/2 minute to midnight, they put in number 2, but they remove ball number 1. Okay, they take out ball number 1. So they put in, and they remove ball number 1. Okay, and then at time 3, I'm sorry, at 1/3 of a minute, they put in ball number 3, but they take out ball number 2, and et cetera, et cetera. Okay, so then midnight comes. What balls are in the bag? What balls are in the bag? What balls are in the bag? Somebody says just 1. What does any? Don't look so nervous, everyone. This is just for fun. The answer doesn't matter. Amanda, you said, Elise?
Do you ever reach midnight?
Do you ever reach midnight? That's the thing. Everybody always asks. I always get this question. Like, some people will say, "Time stops. Time stops." Well, why? Why does time have to stop? Yeah, the clock keeps on going. Okay, so tick, 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 the clock keeps on going. Reaches midnight. Does reach midnight. Right? The genies have to go faster and faster. Right? But the clock doesn't stop. They don't somehow stop the time or something like that. Yeah, they just keep the clock does keep on going. Yeah, Amanda, you said one ball. Julia, you look like you want to say something.
No.
No? Anybody want to say something? There's 1 ball? Do people agree that there's 1 ball in there?
Yeah.
What ball is in there?
Infinite.
Can you tell me the number of the ball? Right, so here are all the balls. 1, 2, 3, 4, 5, 6, 7. Can you tell me the number of the ball that's in there, if there is a ball in there? Right. So people are shaking their heads, right? There is no ball in there, right? Because no matter what number you give me, I can tell you when it was taken out, right? I can tell you when the first ball was taken out. I can tell you when the ball number 2 was taken out. I can figure out, when ball number, 3,000,005 was taken out, et cetera, right? I know exactly when the balls were put in and the balls were taken out. Yeah.
But isn't there for every time that one was taken out, there's one put back in?
Yes, but let me ask you, can you tell me the ball that's in the bag? Right? No. Okay. Okay. So to make it a little bit weirder, suppose I do this. Yeah. Okay. Suppose I do this. So here we put in 1 ball, and here we put in two balls, and we take out the last one. And at this point, we put in 3 balls. Whoops. So the 3 came out. We're going to put it back in. 3, 4, 5. But we take out the last one. 5, 6, 7, 8. We take out the last one, and so on and so forth. How many balls are in there at midnight? Infinitely many, right? Infinitely many. Okay. Now, suppose we do the same thing. suppose we do the same thing, but instead of taking the last ball, we take the one with the lowest number. Okay. And we're going to do it like this. So 1, 2, 3. We take out the 1. Okay. But we keep on going. We don't start from 1 again. We just keep on going. So we say 4, 5, 6. We take out the 2. 7, 8, 9, 10. We take out ball number 3, etc., etc. Okay. So we're adding more and more balls, and each time we take out the lowest numbered ball. Okay. So how many balls are in the bag at midnight? Some people are saying infinity. Some people are saying 0. That's great. That's sort of right where I want you. The answer is 0, right? The answer is 0. Because, again, you asked the question, if you tell me that there is a ball in the bag, what ball is it, right? What ball is it? Is it ball number 100? Is it ball number 3? Well, no, ball number 3 was taken out at 1/4 to midnight, 1/4 minutes to midnight. Was it ball number 100? No, that ball was it ball number 99? No, that ball was taken out at 1/100th of a minute to midnight, and so on and so forth. So no matter what number you give me, I can tell you when that ball was taken out. Right? Okay. So in fact, there are no balls in the bag at midnight. Okay, that's just for fun. But it's related to the notion of limit, which is the main topic for today. Okay, so remember, actually, let me start off with something that I'm going to need later. Suppose you know. No. Yeah. Suppose you know you have two numbers, A and B. Okay. And you know that if you look at A minus B, the absolute value of that, then that's smaller than epsilon for any epsilon bigger than 0. Okay. Okay. So the distance between these two numbers is smaller than any number you choose, right? Like A minus B is less than 0.1, A minus B is less than 0.01, is A minus B in absolute value is less than 0.0000000000000000001. I used to do this to my daughter. I'd say, Dad loves you very, 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 and she would get frustrated and say, much, much, much. She was 2 years old or so. Much, 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 much. So yeah, anyway. Okay, so you know that these two numbers are, now she's 8, doesn't play this game anymore. I haven't tried her, but there was some point where she stopped doing it. Okay. Okay. So suppose you have these two numbers and you know that the distance between them is smaller than any number that you choose, any positive number that you choose. What can you say about these two numbers? What can you say about these two numbers? They're the same. They're the same. In fact, this actually forces them to be the same number. If the distance between them is smaller than any positive number, right? Smaller than any, no matter how tiny number, then we consider those things to be the same number. So for example, right, if somebody says, I'm looking at 0.9999999, etc., and I'm looking at 1, right? You say, well, what's the difference between those two numbers? Well, the difference between them, right, if I look at 1 minus that, the difference is smaller than 0.1, certainly. The difference is smaller than 0.01, it's smaller than 0.0001, right? Because if I stop here, I get a difference of 0.0001, right? But I go on from there, right? The difference between these two numbers is smaller than anything I choose, right? And so we consider these two things to be the same. You might think that maybe you don't want to do that, okay? But that's what people do with the real numbers. If their difference is smaller than any positive number, we consider them to be the same. There are number systems in which people don't do that. So you could say, I want to be in a number system where this is actually two different things. That's okay. There are people who do that sort of work. But in general, people don't. Okay, so that's going to be useful later. Okay, so okay, so let's recall what we were talking about: limits. Right? We saw if the limit of f of x was L as x approaches c, and this basically meant that then given any, so remember the picture, right? Here is C, here is L, right? Given any tolerance epsilon, right? So you take any tiny interval L plus epsilon, L minus epsilon, we could find a delta bigger than 0, such that f of x minus L was less than epsilon whenever x lay inside of c minus delta, c plus delta, but was not equal to c. So hold on for a second. Given any tolerance epsilon greater than 0, we could find a delta such that the distance from f of x to L was smaller than epsilon whenever x was within delta of c. Okay, so the picture was this, remember, right? Somebody says, I'd like you to stay, you're telling me that the limit is L. In that case, if somebody says, I'd like you to stay within this distance of L, you can find a place, C minus delta, C plus delta, where all the outputs lie between those two bars, right? And if somebody says, how about for this epsilon, you could find a place where that happened. And you remember, we did it for a particular example, right? And it turned out for that example that as long as, if somebody gave you an epsilon, if somebody wanted you to stay within epsilon of 6, then as long as you stayed within epsilon over 2 of 3, then things worked out. You remember that? We spent some time doing this last time. So this turns out to be the crucial property of limits. Okay, so everybody thinks of limits as this business. Oh, as you get closer and closer, this gets closer and closer. Okay, this is actually the right way to say it. This actually turns out to be the right way to say it, and it's this mathematician named Weierstrass who really is the guy who realized that this is the right way. So Weierstrass basically realized that this is the crucial property and took this as the definition. Okay, so the definition of the limit is this. We take that as our definition. We say that the limit of f of x is L as x approaches c. We say that the limit is this if given any epsilon greater than 0, there exists a delta greater than 0 such that if the distance of x from C is less than delta and greater than 0, then the distance of f of x from L is less than epsilon. Let me write it in English. Yeah.
Just what's the word?
There exists
No, after.
a delta greater than 0 such that,
Oh.
such that,
Mm.
sorry, such that, with the property that, basically, with the property that. Okay, so in English, right, there exists a delta such that for all x whose distance to C is bigger than 0 and less than delta, we have f of x within epsilon of L. Right? To translate these last two lines here. Right? For all x whose distance to C is greater than 0 and less than delta, we have f of x within epsilon. F of x is within epsilon of L. Does this make sense to people? I don't know. Maybe it makes sense or maybe it doesn't make sense. What is this? The distance to C has to be greater than 0. Why do I say the distance to C has to be greater than 0? Why do I throw that greater than 0? Elise.
So what they can't be the same.
That's right, because I don't want to say anything about C itself, right? When we're talking about limits, we don't say anything about the value at C, right? So I don't care, right? I'm only going to say that f of x, something about the values for the x's who are not equal to C, right? So this guarantees that x is not equal to C. Okay, so, right. Okay, let me do an example to show you how we use this. Okay, so this is how one defines the limit. Okay, it's sort of painful, but don't worry, it'll be over soon enough. So, yeah, we won't spend. We're not going to stay here for that long, but it's important. That's the trouble. Okay, this is really important. Okay, so here's an example. Somebody says the limit of 3x plus 2 as x approaches 4 is 14. Okay, that's certainly true, right? That's certainly true. Okay, and you know, so what do we have to show? We have to show that given any epsilon condition, there is a place, there is a delta place where that condition is satisfied. There's a place where that condition is satisfied, roughly speaking. Okay. More precisely speaking, given any condition 3x plus 2 minus 14 is less than epsilon, given any condition blah, there is a delta so that if x minus c is less than delta and greater than 0, then the condition is satisfied. 3x plus 2 minus 14 is less than epsilon. Right, so this part is here. This part is here. This part is here. Yeah, Ali.
Sorry, just the last sentence here.
Where that condition is satisfied? Okay, so let me show you how you do this. You say, okay, generally you do some scratch work first. Somebody says, oh, I wanted you to show that the limit of this is this. Okay, you say, okay, what does that mean? That means that if I am given this sort of condition, then I can find something like this that forces that. Okay, and you say, okay, you look at the condition. Here's how you do it. You look at the condition, and then you just do some algebra. You say, well, look, this is 3x minus 12. That's the same thing as this. I'm going to consider the epsilon condition. This epsilon condition is the same thing as saying this. Right? Right? That's the same thing as saying this. Or let me make it a bit slower. That's the same thing as saying this. Right? I just factored out the 3. That's the same thing as saying this. Right? The absolute value of a product is the same thing as the product of the absolute values. Absolute value of AB is the absolute value of A times the absolute value of B. Right? And I'm going to get rid of the absolute values on 3 because the absolute value of 3 is just 3. Okay, so I erase the absolute values here. They tell you never to do that when you're teaching, but I'm going to do it anyway. Okay? Okay, so remember what we're trying to do. We're trying to find an epsilon so that, recall, we want a delta so that this implies the epsilon condition. Okay. Now look at the epsilon condition. What is the epsilon condition? The epsilon condition turns out to be the same thing as this condition. Right? Just divide everything through by 3. The epsilon condition, after various transformations, turns into this thing. Right? That basically tells you what to take as your delta. Right? So take delta as epsilon over 3. Okay, so you do your scratch work, and then you write it up. Let me write it up over here. Okay, you say, well, Given epsilon greater than 0, we want delta greater than 0 such that if x minus 4 is less than delta and greater than 0, then f of x minus 14 is less than epsilon. Well, take delta to be epsilon over 3. For then, if x minus 4 is less than epsilon over 3, right, is less than delta, namely epsilon over 3, we see that, going backwards, right? If x minus 4 in absolute value is less than epsilon over 3, then blah, 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 this is true. That, right, 3 of this is less than epsilon. In other words, 3x minus 12 is less than epsilon. In other words, 3x plus 2 minus 14 in absolute value is less than epsilon. Yeah,
So
Sarah.
do you know that epsilon over 3 equals delta? Don't you just know that they're both greater than the absolute value of x minus 2?
We take our delta to be epsilon over 3.
Okay.
We say let it be. Let delta be epsilon over 3.
Okay.
And it turns out that that one will work. That
Okay.
delta is going to work for us. So remember the game, right? You're trying to show that somebody gives you this epsilon condition. Okay. Somebody gives you this epsilon condition, and you're trying to find a place where the epsilon condition is satisfied. You do your scratch work, and it turns out that taking this delta is going to do it for you. You say, okay, well look, if I take my delta to be epsilon over 3, if I take my delta to be epsilon over 3, then blah, 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 3x plus 2 is within epsilon of 14. And so I've shown it. Maybe let's do another example. Yeah, you guys choose an example. Choose an example. The limit of, and just make it a linear example to make it easy. Choose an example, please. Somebody give me some linear function. Julian.
The limit of 5x minus 2 equal
As x approaches
3.
3. So 13. Okay. So probably some of you will know already what the delta is going to be. What's the delta going to be? Okay, give it a try. See if you can do it. See if you can, do the scratch work, figure out what the delta has to be. Just do this first part. Do the scratch work and figure out what the delta has to be. Isaac.
There's no absolutes and there's no epsilon. There's no absolutes in that, there's no epsilon on the other side of it. Makes it complicated.
Yeah. So, right, you have to translate this, right? What does it mean, right? It means that you want to show that given any epsilon greater than 0, there exists a delta greater than 0, such that if x minus 3 is less than delta and greater than 0, then the function minus 13 is less than epsilon. Right? So you have to translate. first, and then do the scratch work. Okay, I'll go walk around.
Just remember, because I'm not doing it, that's my
I think it's just you have to like keep it down. It's always to like X minus.
Yeah, because
Otherwise, it's like you just have to try to.
you're trying to prove that X minus 4 is toward the limit or C,
And in this case,
the delta is that's what is to translate as epsilon. Because you're trying to simplify it down so that the absolute value of X minus 4 is less than
Isn't it over? That's fine. So we're going to find good numbers. Give it up.
I mean,
Everyone.
I thought if
linear values will work out.
Yeah.
when is it that you can do like just this equation of isn't
Okay, would anybody like to say what they did? So what's the delta? What's the delta? Somebody?
Epsilon over 5.
Epsilon over 5? Epsilon over 5 will do. And how do you figure it out?
Just go through all this.
Go through all the steps. Just go through all the steps, he says. Okay, well, so you say, well, let's look at the epsilon condition, right? Oops. Yes, that's right. You take the condition, right, and then you reduce it. Right? So this turns into 5x minus 15. So this is the same thing as, so this mark means is equivalent to. If I read it like this, means it implies that, but this means that is exactly equivalent to. That this implies this, and this implies this. They're the same statement. Okay. This is the same statement as, which is the same statement as, right? And so you see that as long as x is within epsilon over 5 of 3, right? So as long as x is within epsilon over 5 of 3, we see f of x is within epsilon of 13, right? This guy is our f of x. Right? So you've done your scratch work, and it seems kind of redundant to write it down again, but generally you write it down forwards. Okay, wait for 1 second and then I'll write it up. So you say, well, okay, so given epsilon, take delta to be epsilon over 5. Then, if x minus 3 is less than delta, we see that 5x minus 3 is less than epsilon over 5, is less than epsilon. In other words, 5x minus 2 minus 13 is less than epsilon. Right? So the limit is indeed 15. Okay, because we found, no matter what tolerance you're given, we found a delta that works for it. Right? And the picture is that the picture is like this. The slope of this line is 5. The slope of this line is 5. Right? So if somebody says, oops, if somebody says, I'd like you to stay, at 3 you're at 13, I'd like you to stay within epsilon of 3. Well, you would say, well, I'm going to move only epsilon over 5, right? Because my slope, the slope of my line is 5. So if I move epsilon over 5 away, if I move more than epsilon over 5 away, I'm going to move more than, my output's going to jump more than epsilon, right? Just by your understanding of slopes. Slope is velocity. Those of you who know the physics, right? The speed of this guy is 5. So if you want him to stay 1 unit away, well, you'd better stay a fifth of a second away here, right? A fifth of a unit of time here, right? If you want this guy to stay, stay within epsilon distance, well, then you can only move epsilon over 5 units of time down here. Amanda, what's your question?
Are all the numbers going to work out so nicely, or?
Yes, they will for linear functions. So this is, it's true. This is just like a very simple kind of example. In others, sometimes, it won't. If it's something more complicated than a linear one, then no, it won't. But this is just to show you how it goes and how you start thinking about it.
How does this prove that 13 is the limit?
So remember what it means for 13 to be the limit. For 13 to be the limit means that no matter how close somebody wants you to be to 13, you can find a distance to 3 where that is satisfied.
Okay.
Okay, and what we've done is said, well, if somebody wants you to be within epsilon of 13, just take your delta to be epsilon over 5, and that will work for you. Okay, so we've done it for whatever. If somebody says, I'd like you to stay within 0.1 of 13, all you'd say was, well, I'm going to take 0.02 as my delta, and that satisfies you.
So that's just like the idea that given any epsilon, that's a proof of a limit? Or
That's right.
Okay.
So this is how you show that the limit is 13.
Okay. Is this the way you want us to prove?
Yes, I'm afraid so.
Okay.
Yes. Yes. Yeah. So this is actually how you do it, and it gets trickier. But in a few minutes, we'll give you some tools that will allow you to sort of avoid this forever, or maybe not forever, but at least for a few weeks, maybe for the rest of this course. Evan.
Can we use like a right and left-sided limit to prove a limit also?
But you would have to go through this sort of thing. You see, how do you prove a right-handed limit? Well, you have to do this sort of argument as well.
But like it's a little quicker, right? Because if it's a linear function, it's the same for both sides. It actually won't be any quicker. It'll be basically the same amount of work. Right.
Yeah, it'll be exactly the same amount of work. Or it could be double, depending on how you write it.
Okay.
Right? If you do right-handed and left-handed limit, well, then you have to do 2 limits.
Yeah.
Right? Here you're doing the 2-sided limit simultaneously.
Okay.
Okay. Any questions on this? Okay. So okay. So there's so you've taken the idea of limit and you change it into this mathematical thing. Okay. Once you have this mathematical thing, then you can show certain things happen. Okay. So so consequences or properties of the limit. Properties of the limit. Okay. So it's basically does the limit defined in this way, behave as it ought to? Okay, and the answer is of course yes. Okay, so there's one result which is on uniqueness. And it basically says this, if the limit of f of x is L and the limit of the same function is M, then you have to have L and M the same number. So it's basically saying that if you go into one room and you find the limit of a function, and your friend goes into another room and finds the limit, then you're going to come up with the same thing. It's just that there's only going to be one limit. With this definition, there's only going to be one limit. I think I'm not going to explain that for right now. Let me get on to the next thing, which is you could call limits and arithmetic. Okay. So say that the limit of one function is L, and the limit of this other function is M as x approaches the same point. So you have one function that approaches one value, you have another function that approaches another value. Then the limit of the sum of these functions as x approaches c is going to be what? What should it be? L plus n. Don't put it on, but L plus n, yes. Right. The limit of the sum is going to be the sum of the limits, right, in English. The limit of the sum equals the sum of the limits.
Behind you.
Yeah, I just.
Also, the limit of the product is going to be what? Somebody else? Well, the product of limits. Maybe I should say it's okay to blurt it out. The limit of the quotient is going to be the quotient of the limits if m is not zero. And last, the limit of some number times your function is just going to be that number times the limit. So this is basically saying that the way limits interact with arithmetic is the way you would hope it would, right? That if you take the sum of functions and you take the limit, well, you're just going to get the limit, the sum of the limits, right? The limit of the sum is the sum of the limits, and the limit of the product is the product of the limits, limit of the quotient is the quotient of limits, and limit of a number times the function is going to be the number times the limit. Yeah, Becca.
What is the symbol in the fourth?
Symbol in number 4. Alpha.
Yeah. Oh.
Alpha. So where alpha is some number.
A constant?
Yeah, a constant. Yeah. So if you have, that the limit of x as x approaches c is just c, right? The last one says that the limit of some number times x is just going to be that number times the limit. Right. If you multiply by a number, then the limit gets multiplied by that same number. So just things that you would think ought to be true. Okay. as an example of the second one, the limit of x as x approaches c is c. So what's the limit of x squared? Well, the second property says that it should be the limit of x times the limit of x. Right? The limit of x times x should be the limit of x times the limit of x, right? So that's going to be c squared, c times c, c squared, right? And so on and so forth, right? If I have the limit of x, to the 10th power as x approaches c, well, that's just going to be c to the 10th, et cetera, et cetera. Right? If I have the limit of x to the 5th plus x to the 4th as x approaches c, well, I use the first property, right? Saying this is going to be the limit of x to the 5th as x approaches c plus the limit of x to the 4th as x approaches c. That's going to be c to the 5th plus c to the 4th, right? By the first property. If I put in some numbers here, right? Pi and 7, say, right? Then by property 4, I know that this is going to be pi and 7, so I get pi here and 7 here, right? And so on and so forth. And so what you see is that this thing gives you control over limits of polynomials, right? This thing basically tells you about limits of polynomials. Okay, we're going to stop there for today.